The study of light provided important information about the electrons in the atom. In the early 1600s, Isaac Newton suggested that light consists of tiny particles, while at the same time Christian Huygens suggested that light consists of waves. So the controversy began. Is light a wave or a particle? As late as the early 1900s, there was still no resolution to the dilemma. A German scientist, Max Planck, could only explain what he observed in his experiments if light were viewed as a stream of particles, or bundles of energy that he called quanta. In other experiments, only if light were viewed as a wave could scientists explain what was observed. Although we won't go into the specifics of the various experiments these scientists conducted during the study of this course, suffice it to say that scientists were puzzled. Just what is the wave description of light? And what is the particle description of light?
The wave description of light includes several wave features, such as wavelength and frequency. Wavelength, which is represented by the Greek letter lambda, is the distance between corresponding points on adjacent waves. For the sake of simplicity, we usually say that the wavelength of a wave is the distance from one crest to the next crest, or the distance from one trough to the next trough. Frequency, represented by a script lowercase f, is the number of waves that pass a given point in a given time. Normally, frequency is measured in the unit called hertz, which simply means per second. Mathematically, the frequency and wavelength of a wave are inversely proportional. In other words, as the frequency of a wave increases, the wavelength of the wave decreases. We write this relationship mathematically as c equals the wavelength of a wave multiplied by the frequency of that wave. The letter c represents the speed of light, which is a constant that is equal to 3 times 10 to the 8th meters per second in a vacuum.
We can actually use this equation, called the wave equation, to solve various wave problems. For example, what is the frequency of light with a wavelength of 6.0 times 10 to the negative 7th meters? Because the speed of light in a vacuum is always 3.0 times 10 to the 8th meters per second, we know c as well. Using the wave equation, c equals wavelength of a wave multiplied by its frequency, we simply substitute our known values into the equation and solve. We know that the speed of light is a constant equal to 3 times 10 to the 8th meters per second. We also know that the wavelength of the wave is 6.0 times 10 to the negative 7th meters. Now, we solve for the frequency and find the answer to be 5.0 times 10 to the 14th hertz. Let's try one more. What is the wavelength of yellow light if the frequency of that color of light is 5.0 times 10 to the 14th hertz? The speed of light is a constant, so we know that c is 3.0 times 10 to the 8th meters per second. We have been given the frequency of the yellow light, so we simply plug the numbers into our wave equation and solve. Remember that the hertz simply means per second. Voila! The wavelength is 6.0 times 10 to the negative 7th meters. You'll have a chance after this program to practice some of these problems yourself. Now, let's look at the particle description of light.
Max Planck could only explain the results of experiments he performed if he suggested that energy exists in small bundles or particles called quanta. Planck proposed that a quantum of radiation is the minimum amount of energy that can be lost or gained by an atom. Planck also suggested that the energy of a quantum of radiation is equal to the frequency of the radiation emitted multiplied by a constant known as Planck's constant. From this equation, we can see that the energy of light is directly proportional to its frequency.
What is the modern view of light? How is this dilemma of light as a wave or a particle to be solved? Apparently, some experiments can only be explained if light is viewed as a wave, while others can only be explained if light is viewed as a particle. Our modern view of light is attributed to Albert Einstein, who in 1905 introduced the idea that light has a dual wave-particle nature. Although light has many wave-like characteristics, it can also be thought of as a stream of particles, or quanta, which Einstein called photons. Modern scientists suggest that the nature of light depends on the experiment.
Let's examine the nature of light. Watch as the student performs flame tests. She places a small amount of a chemical on a nichrome loop and then burns the chemical in the flame of the Bunsen burner. Different chemicals will produce specifically colored flames. Copper compounds produce a blue flame. Sodium compounds produce a yellow flame. Strontium compounds produce a red flame.
A beautiful fireworks display is possible because of this very same concept of excited atoms that have absorbed energy, then given off visible light as they drop back down to the ground state. Just as in flame tests, in fireworks, barium compounds produce green light, sodium atoms produce yellow light, and compounds of strontium produce red fireworks. Fireplace logs or pine cones that burn various colors are another example of this phenomenon. Manufacturers simply treat the logs or pine cones with certain chemicals so that a colorful fire will result. The light emitted by an element when its electrons return to a lower energy state can be viewed through an instrument called a spectroscope. A spectroscope works like a prism. If I look through this spectroscope at the flame produced during our flame test, or at a gas excited by electricity in a discharge tube, the light is separated into the various colors it contains.
The science of studying visible light through the use of a spectroscope is called spectroscopy. Each colored band of light represents the energy that is released by an electron when it returns from an excited energy state to a lower one. The energy of each band of colored light is equal to the difference between the original and final energy levels of the electron. These bands are called spectral lines and are the fingerprints of the element. No two elements have the same set of spectral lines, just as no two people have the same fingerprints. We call this set of spectral lines the bright line spectrum of the element.
Today's modern picture of the atom still goes a step further than Bohr's energy levels. Like Bohr's model, the modern model of the atom predicts energy levels for electrons. But unlike Bohr's model, the modern picture of the atom doesn't describe the exact path an electron takes around the nucleus. Instead, it is concerned with the probability of finding an electron in a certain position.
Today, rather than